In this video, I want to talk about testing a hypothesis about a population proportion. Now, if you've been in a traditional statistics class, specifically an introductory statistics class, you've probably learned about testing a population proportion, but you did so using approximations and using the normal distribution. And this is different than what we're going to do today. We are going to look at an exact test for a population proportion. And we're going to do so using fewer conditions than those that you learned about when you learned about it using the normal distribution. We're not going to have as strict a conditions, meaning it's easier to ascertain that what you're doing is correct and yielding correct probabilities. Now, this is all based upon the binomial distribution, which is based upon the binomial formula, based upon the binomial coefficient, based upon Bernoulli events, which in turn is about dichotomous data. And there are videos about each of these. If you have not yet watched those, you may want to do so that you're prepared for what we're going to do in this video. So buckle up, let's get going. First, let's review the steps in hypothesis testing. The first step is to make sure that you have met the conditions for valid inference. And if you have met those conditions for valid inference, then you can move on to step 2, establishing the hypothesis, setting up your tolerance for a type 1 error. Sometimes that tolerance is based upon an industry standard, like 0.05 is a common one. And then you determine the decision rule. That is, under what conditions will I reject the null hypothesis? Under what conditions will I retain, that is, not reject the null hypothesis? Once you've established all of this, you're ready to collect the data. And you collect the data, you make the observations, you align these with the decision rule, and then decide, will I retain or reject the hypothesis? Remember, that hypothesis is about an unknown population parameter that we cannot know because we cannot look at the entire population. What we can do is draw some observations out of that population, but we're using those to make a hypothesis and test a hypothesis and make a determination, something about that population parameter within some level of confidence that we set. So now specifically, when we're looking at a population proportion, what do? Well, step 1, assess the conditions for valid inference. And if you recall from previous videos, we have to select units at random from the accessible population. I really am interested in a target population, but we don't have access to the whole target population. So instead, we have that population that's accessible to us. That is, not the sample. The sample would be what we actually observe, something bigger than the sample, something that we can actually draw units out of for the sample, but also not the entire population of interest. This is the accessible population, and we select them at random. And then we see that the observations are independent of one another when we make those observations. We don't want to have overlap when we're observing of one unit with another. Now, the reason we select at random from the accessible population is for 2 reasons. 1, maintain the exact probability of inference to the population. That is, when we say we're 95% confident, we want to be 95% confident, and that relies on random selection. But there's another thing that this does, and that establishes the independence of our units. And when we observe independently, that continues to maintain the independence of the data obtained from these units. Why is that so important? Well, if you've watched the previous videos, you know that when you have independent units, it allows you to multiply together probabilities in order to look at a joint collection of outcomes. And so that's why that independence is important. Without it, we cannot figure out that probability. So those are the conditions for valid inference. Notice that they're pretty minor. It's pretty easy to maintain independence of your observations. This is a lot different than what you may have learned about with your very first hypothesis test about a proportion, in which you assumed a certain sample size, in which you assumed that the population proportion was something near 0.5, or if it varied from 0.5, that you had to take an even bigger sample size. And even if you met all those conditions were based upon a model distribution, not an exact distribution, so that your probabilities you calculate are based on an approximate model, not on the exact distribution. We're going to use the exact distribution. So now we go to our second step. Establish the hypotheses, set the tolerance for a type 1 error, and determine the decision rule. Here I've written out the null and alternative hypotheses, and I've done it using a generic letter C, that is, to stand for anything that's reasonable. Now, proportions can only be between 0 and 1, so C has to be between 0 and 1, but you can hypothesize any value between 0 and 1 for your population parameter, here denoted as the Greek letter pi. The alternative here is written as a one-sided alternative, which I believe most often matches what we're doing in research. We're looking to see things like, does a treatment work? Not to see if a treatment changes things, but does it work? And so we have here a one-sided hypothesis. There is an equivalent two-sided hypothesis, but right now we're going to stick with this for learning about hypothesis testing. So we have some value, and we're wondering, does pi exceed that value, or is fact pi equal to or perhaps less than that value? So for example, what if we put in the value 0.5? If you think about having a treatment in which you look to see if individuals improve based upon the treatment, well, you would expect just by chance half to get better, half to get worse. So 0.5 is actually a nice example for a baseline for a null hypothesis. It would imply that if we apply a treatment to members of a sample, that if nothing is going on, we would just by chance expect to see about half of the scores change upward and half the score change downward. That is, having nothing to do with the treatment, more or less a random fluctuation. Whereas if we have an alternative hypothesis of pi greater than 0.5, that matches our research hypothesis. I distinguish statistical hypotheses from research hypotheses. A research hypothesis is what the researcher is projecting is going to happen based upon their theoretical model. So if you develop a treatment, you believe that treatment's going to be effective, otherwise you would not have developed that treatment. So if in fact the treatment works, we would expect that when we apply the treatment, more than 50% of the scores would go up. So pi would be greater than 0.5. Here I'm using pi to indicate the proportion of individuals that appear to be helped by the treatment. So here are examples, but again, remember that we don't have to use 0.5. We can use 0.7, 0.8, 0.3. We can use anything. Well, why would we use those other numbers? Well, what about, for instance, if you have a vote in which at least 60% of the population needs to vote for a particular outcome in order to have something happen, like maybe a constitution be changed? Well, in that case, then we'd want to use 0.6 instead of 0.5. So really that number relates to what our specific research hypothesis is. Now we have to set the tolerance for type 1 error, and we can set it at anything. 0.05 is something you have probably seen many times, most of the time, the overwhelming majority of the time in the past, but it doesn't have to be 0.05. But I'm going to go ahead and use it because I'm going to stick with a societal norm. That's typically what we set, at least in the behavioral and social and medical sciences. We set alpha, our nominal type 1 error rate, meaning the maximum allowable type 1 error, the maximum tolerance I have for a type 1 error. And remember, a type 1 error means rejecting a null hypothesis when we should not. And that's considered a serious error because it leads us to say things like the treatment works when it doesn't. And then we determine the decision rule.